Hey everyone, and welcome back to another CTF Writeup video. This is San Diego CTF, hosted by University of California, San Diego. And in today's video, I'm going to be covering the Pwn Challenges, and there are 4 of them. Like usual, I'm going to go pretty fast, so if there's any questions, feel free to leave it in the comments. You can message me on Discord, I'm Conrad, or Twitter, I'm also Conrad. With that, let's get started. The first challenge is Pwn Turtle Shell. It says a turtle without its shell is a sad sight to see. We're given a netcat port, a Docker file, and a binary. If we look at the Docker file, we can see it's 1804. This could be useful if we needed libc or something, but we don't for this challenge. If we take a look in Ghidra, let's jump to main. It's going to do some buffering. It's going to say something to make the turtle come out of its shell. It's going to read it, and then it's just going to cast it as a code object and then execute it. So basically, this is definitely a baby challenge. We just need to supply this program some shellcode, and it'll execute our shellcode. So that's simple enough. We're going to use Pwn tools. I'm not going to cover this every time, just the first time. We import a bunch of stuff. I ignore warnings. We load the ELF binary. We set some context so that Pwn tools knows the architecture and bits. This is AMD 64. We set log level to debug so we get everything. And then I use tmux for terminals because I run everything in Docker. And if I do this tmux split window, I'll have like my normal bash shell and GDB side by side, which is nice. We grab libc, we don't actually need it. We start the process, and then after it asks us for a shell, we're just going to send it a shell. Thankfully, Pwn tools builds a shellcode for us. So we're doing Pwn shellcraft, so build a shellcode for just running shell, and then you have to wrap that in a pwn.assembly because it just gives you the assembly. So you generate the actual shellcode for it, and you send it, and we should just get shell. So let's do Python 3, solve.py. Oh, it helps if I'm in an Ubuntu container. We'll just do normal Ubuntu. It was Python 3, solve. Cool, this is the shellcode that was generated. We can see it's just going to call exec_ve, path bin shell, arg shell, and environment 0, or null. But at this point we should have shell, so we do. Let's try running it on remote. And there's the flag. Wow, you made the turtle come out of its shell. The next challenge is Pwn multi-printer. It says the first step to getting rich is printing money. We're given a netcat port, a Docker file, and a download binary. So if we open up in Ghidra, there were 2 bugs with this one. First, we have to bypass some kind of strange logic where we're like withdrawing money from a bank or something, and eventually it'll exit once the bank has a certain amount of dollars or you have a certain amount of dollars. There's 2 of these challenges. I forget which one is which, but basically you just supply it negative money and eventually it'll wrap around and you'll bypass this check. The real bug is down here. It's a printf. So it's going to do a fgets on this in buffer from standard in for 100 bytes, and then it'll do printf. Thankfully, the printf exploitation for this challenge is pretty simple. If we scroll up a little bit, we can see it's opening up flag up here. So say this is flag file pointer, and then it's going to read in flag. So what's interesting, so it's going to read in 0x2d bytes from the flag file pointer. So this means the flag exists on the stack. And because of that, when we do this printf exploit, like we don't have to do any %ends or anything complex. We just need to print out the contents of the stack, which is super nice and easy. We just do %p or %x, and we should just be able to leak it. So this is the solve script. Like I said at the very start, you have to do that negative balance thing. You just pass it minus some large number and it skips that part. For the actual printf exploitation, I just joined this together. So this is going to create a string where I do a %number $p for every number between 1 and 25. So that'll print all 25 arguments on the stack and give us the hex for them, which is exactly what we want because we know somewhere in there the stack should, or the flag should be there. And then we're going to receive the line. We'll print it out. Since it'll be in hex, we just need to decode it, but not everything is like valid hex, so I do this like little strange logic where I just read it all in, I decode it, I do a try catch in case like it's a null or something, or nil, I think is what it says. And in there, somewhere in there, the flag should exist. And we also have to reverse it because of the order. But we can give it a shot, see if it runs. Python 3, oops, we need to be in Ubuntu. Python 3, solve. And cool, so we get back, this is what we're sending here, the %1, $p, $p, %2, $p, all the way to 25 or 24. and it says, wow, you said, and so we can see this is probably a stack pointer. We got a libc, some value, another libc, just a bunch of interesting stuff. But this here looks like ASCII. We can see 66, 5F, 73, like these are all kind of ASCII values. And then we get back, and this is where we parse it out. Oops, didn't mean to do that. This is where we parse it out, and there's the flag. So SD, damn, you found a crazy amount of money. The next challenge is Pwn tROPic-thunder. It says, I hope this isn't your first rodeo. We're given a netcat port, a Docker file, and a download file. It's also important to note that ROP is capitalized here, so we can guess that we have a ROPing challenge. If we look within Ghidra, it's a nice simple binary. It's going to do some buffering. It's going to set up setcomp, which we need to look at in a second, and then it's going to do a quick puts. Then it's going to read in 512 bytes into a buffer that's only 112 bytes, so we have an easy buffer overflow, and then it'll return. So nice and simple. If we look at the setcomp, it's going to be disabling two different syscalls that we can see here. So I'm going to copy those out and put that in the solve script right here, and we'll look at those in a second. The other thing we need to look at is the protections on the binary. Make checksec. You can see there's no pi, there is NX, and partial rel-row. So that kind of puts everything together so far, except for the setcomp rules. But basically, if NX is enabled, we're not going to be doing shellcode, so we definitely are going to be ROPing, which is what the challenge said. Since pi's not there, that makes it a little bit easier. As long as we can find good ROP gadgets within the binary, it should be pretty simple. We probably only need to call this program once, or call main once. Sometimes if ROP isn't, or pi isn't enabled, sometimes you have to find a leak somehow and then jump back to main and do multi-shot, but nice and simple for this one. And let's take a look at the syscalls. So we get OX3B and OX142. So this is the website I use. It's Chromium Google source, and it has all the syscalls in a nice clean table. So we're looking for 3B. If we scroll down, this is syscall 3B right here, and we can see it's exec_ve. So, and then if we look at the other one, what is it? OX142, exec_ve at. So basically, for this challenge, they want us to write ROP code, but we're not allowed to just spawn a shell. I guess that's too easy. So we need to write ROP code, but pi isn't enabled, so the main ELF binary has static addresses, which is nice and simple, and we have a huge buffer overflow, so we have plenty of space. The solution I did for this was, first I calculate the offset, so we need to read like 112 bytes or something like that before we can actually begin. And so you can just do a Pwn cyclic and then see where it crashes within GDB, and from there you know this is how many bytes you need until it starts, or you can put your ROP code. This is the actual ROP code. So the idea behind this is we're going to open a file, then we're going to read from the file, and then we're going to print out the file. To do that, first we do this read call. So it's tricky to pass strings when doing ROP code. You need like a write what where gadget, or you just have to be clever with your gadgets. It's way easier just to call read and read from standard in and put the data into some address. And so for us, you can see there's two different send calls here. So first we're going to send the ROP chain, and then we're going to be sending this extra input. And this extra input is going to get read by this read call right here. So basically after this executes, it's going to read in 256 bytes into the data section. That'll now contain this string. Then we're going to open it. So we're going to pass that that buffer, and it's going to open it with standard permissions. And then we're assuming the new file descriptor is going to be 3. If it wasn't the case, you might have to find a gadget for moving RAX to RDI. No, RAX to RDX. I think could be wrong though. We'd have to look at the syscall table. I mean, we can look at the syscall table if you had to find the gadget yourself. So after open's going to put the file descriptor number as RAX, and then when we do a read, we need it to be an RDI. So this is the file descriptor. So we would have to find a move RAX to RDI gadget. But thankfully it's just 3, and it was that way for local and remote, so we didn't have to worry about that. So we're going to read in from the flag file into the same buffer. I'm just reusing the buffer. We're going to read in 256 bytes, and then we're going to print out the contents. And that was pretty much it. So we're running it locally. Let's give it a shot. Make Ubuntu, Python 3 solve. It's loading everything in, and we get flag YOLO, which is just my local one. So now we can try running it remotely. One thing we need to do differently with remotely is we need to send the correct flag path. Thankfully, they gave us a Docker file. And so we can see it's doing copy flag into home user, so we know where the flag exists on the remote system. So it's just home user flag, and that should be everything. So we'll give it a run, and there we go. And it says, I watched tROPic-thunder while making this challenge. The last challenge is Pwn multi-printer. It only had 8 solves, so not a highly solved challenge, and I didn't solve it myself either. It says there's a few more steps to getting rich than I let on last time. We're given a netcat port, a Docker file, and the binary. Like I said, I didn't solve it, so I'm referring to 2 different write-ups, one by Crazy Man and one by Ash. They both put their solve scripts in Discord, and the challenge author also confirmed that that was the intended solution. And the intended solution is you do have to brute force. You have about a 1 in 4,096 chance of getting it correct. So with those 2 write-ups, I was able to kind of go back and write my own solution after seeing what the correct solution was. And so I'm pretty much just going to be covering that. But like I said, you can read the other 2 write-ups. They're both in Discord. Like I said, this is Crazy Man's solution. A very good solution. I learned something very interesting from their solution, this mbrute force command, part of Pwn Tools. I'll talk about it a little bit later, but super cool. It does multi-threaded brute forcing for you. Normally I have to write it myself, but I didn't realize Pwn Tools already has one. And Ash's solve has a lot of comments. And I learned also something very interesting from here, which again, I'll be talking about later, is one note about using the positional arguments is once you use it, the arguments are saved. So to use a corrupted stack pointer, you can't use the positional arguments. This slowed me down for a long time. And so I'm very thankful for that comment too. But anyways, let's take a look at the actual challenges. So this is it in Ghidra. It's pretty much the same as Money Printer 1. Again, it does this weird thing where like the bank has some money and you have some money and you just have to give it a negative number. It is what it is. After that, we get the fun stuff, and so we have a printf. Last time on Money Printer 1, the flag was loaded on the stack, and we were just able to read it off the stack. In this case, the flag is not on the stack, so we have to be a little bit more clever. But again, we get a printf exploit, we get 100 bytes. Pi is not enabled, so we know where the main elf section is, but we don't know where libc is. And somehow we need to get shell or do some clever, I guess we wouldn't really be ropping since we have printf, and there is no buffer overflow. So really we just need to be very clever with our printfs. And so as I'm sure you know, we can do %n to write different places, but the tricky problem part of this challenge was there was no obvious place to write. We don't have a stack leak, so we don't know where anything is on the stack. Actually, let me back up. There's a couple of obvious targets. Like for example, overwriting the global offset table. So we know the address of the global offset table, but there's no calls here that would reference the global offset table. Like there's this stack check fail, which is actually on the global offset table, and we actually will be using it in a second. But if you overwrite this with something else, it's just you're not overwriting the canary, and you can't just like do a %n and overwrite the canary, because if you remember, a %n takes in a int pointer, so we need something that would be pointing to the canary, and there's nothing that points to the canary. I searched all over the place. I spent a full day trying to do this challenge, trying to find something that was pointing somewhere. Like I was looking at like fsop and just all the different pointers. I was combing through the read-write section, the data section, looking for something that might give us an edge, but like I said, I didn't solve it. I was also dumb. I thought about brute forcing it, but I did the math wrong, and I was thinking it was going to be a 16-bit brute force, not a 12-bit brute force. But anyways, this is the solution. So instead, what we're going to be doing, the 2 people had slightly different solutions. I think Ash was overwriting the return address on the stack. I don't think they do stack check fail. Canary, yeah. They're just overwriting the return address on the stack, and so that we can jump somewhere we want. Whereas Crazy Man and the solution that I'm about to cover, we both actually try to corrupt the canary so that it calls this stack check fail, and that we can rerun the program. This challenge is trivial if we had leaks. Like if we knew the address of libc and the stack, we can just jump to a 1 gadget and it's instant win. There's just the problem is we only get to execute this printf once, we don't have the leaks, and we have no way of controlling execution. So what I've kind of hinted at a couple times now is the solution is, what we're going to be doing is we're going to try to guess where the stack is. Sorry, the canary is on the stack, just by guessing, and we can be a little bit clever about it, but it's still pretty tricky. And it's trivial to I say trivial, but we can easily overwrite this this function because it's on the global offset table with anything we want. And so what we're actually going to do is 3 things in our first call. We're going to try to corrupt the canary. We're going to overwrite this, with main, so we get to call this function again, and we're also going to leak some values. When we call it the second time, if we leak values correctly, we should have a stack leak and a libc leak, and from there we can just overwrite the return address with a one gadget. And that was pretty much the solution. So this is the solve script going through. I'm not going to cover all of this. Basically, I'll just kind of give some insight. I think really to like learn this printf stuff, you really just got to play with the stack, and I just don't think it's that exciting on video. But basically, we're going to first do the integer underflow, same as last time. I'm going to talk about the little tips and tricks in this, but again, I'm not going to open up the debugger and go line by line because I don't think anyone finds that interesting. So first thing I do is I do 24% Cs, and this is interesting. Kind of what I hinted to with the ashes solve. Basically, to overwrite the canary, we're going to be looking for this very interesting primitive on the stack, and what we're looking for is a pointer to a pointer on the stack. And so what we're going to do, so we have a pointer to the stack. What we're going to do when we write the first pointer, we can overwrite the first pointer, we're going to change the relative address of this pointer, and as long as it's pointing on the stack, we're just going to overwrite the last byte or the last 2 bytes, so it just points a little bit somewhere different on the stack. Like I said, what made this challenge tricky is we don't actually know where we want to point, but it's possible to brute force it, and every once in a while, like if you just change the last 2 bytes of where the second pointer is, eventually it's going to point at the canary. So to kind of repeat, we're going to overwrite this first one, and since it takes in a int star as an argument, it's going to overwrite the 2 bytes here, and so that this stack pointer points somewhere else. Then we're going to write to this stack pointer, because this pointer exists on the stack too. We're going to write a value that'll corrupt the whatever it's pointing to. Hopefully it's pointing to the canary. And once the canary is corrupted, we can get execution. So we have to do 2 separate writes. What's a little bit frustrating, and I got stuck on for a while, is if you use a positional argument to overwrite this stack pointer, when you try to, it actually for some reason like saves the positional arguments and doesn't update it when you try to overwrite this one. It actually uses the old stack pointer for this one for some reason. So I think this is 25 and this is 51. Yeah, address 25 and address 51. So if I overwrite 25 so that this is pointing somewhere new, it'll use the old value of 51. I don't quite understand why. Like I said, Ash mentioned this in their solve script. Oh, by the way, it's Ash with a $S. I think it's Ash. Again, I don't quite understand why, but that's fine. There's a way around this. So instead, you can push up the stack argument that it's using by just throwing a bunch of stuff away. So we're just going to do a bunch of %Cs, and this is going to print character for the first 24 of them. And then on the 25th stack element, we'll actually do the %HN. This actually does 2 things too. When we do this, we're actually writing 24 bytes to the stack. The canary address, it's going to be 7F blah 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 blah. I should use numbers, something like this, but it'll always end in an 8. And this is where I was kind of getting my math wrong. I was thinking that to brute force this, we would have to do 16 bits, but since it always ends in an 8, really we're only brute forcing these, and so it's just a 12-bit brute force, which is a 1 in 4096. But anyways, so this is what this is going to do, is it's going to push this up. It's going to write 24 bytes, which is 0x18. It's going to point to the pointer somewhere else, and then we're also going to write that to the canary. No matter what, writing the low bytes to the canary will always corrupt it, so we can write anything. We're just going to write 0x18 to it. After that, we do some leaks. So this is the first leak. I forgot the order of this. I think this is canary. Actually, it should be down here. That's canary, libc, and then stack. So we just have 3 different pointers. I don't technically need to leak the canary. I just think it's interesting, and then you can actually see when it's corrupted. The next step is we need to overwrite the stack check fail with main. So that way, if we do corrupt the canary, it'll jump back to the start of main, and we get to do everything over again. To do that, you calculate how many bytes have been written, and you see where main is. I think main is at 0x7E7 is the last 2 bytes. And you just find the difference, and the difference ends up being 1950. And then we overwrite this positional argument, and you calculate this positional argument. It's a little bit tricky, but basically this is the argument right here. So you do this by just sending a bunch of A's and then doing %P's, and you can kind of see what address corresponds to this. So when we send this as a payload, this corresponds to argument 19. A little bit confusing, but I don't like printfs, but they're super powerful. Anyway, so it'll write the number of bytes written to this address. This address is the global offset table. So now this entry will contain the address of main. Cool. So we're going to send everything. When we send everything, when we read the response, we'll get all of our leaks. So the first leak is a canary. We don't actually need it. I just like to print it. The next one is a libc leak. You just take the current leak and you calculate, do a VM map in GDB. You can calculate the base, and then you can subtract that. And so we have the base of libc. Then from there, we're going to use, leak the stack. For here, I calculate the current leak and where the return address is, because all we really want is the return address. So when we call it into the next main, when it returns from that and then returns from that, this address will be executed, and that's where we're going to put our one gadget. And then I just grab a one gadget. These were all the one gadgets available. Thankfully, the first one worked. I print out all the variables. Normally, like I said, to corrupt the canary, there's only a 1 in 4,096 chance of getting it correct. So normally this fails right here, and it's just going to throw an error like connection is closed or something. But 1 in 4,000 chance, it'll continue. So we get to send back a large negative number because it does that weird bank math or whatever. And then comes the easy part. We have all of our leaks, so we're just going to say at that stack return address, just put a one gadget there. Since it's a nice and simple format string, we can just have Pwn tools do it for us. So offset 8, if you just send a bunch of garbage, you do like AAA, BBB, CCC, and then do some %ps, you can figure out what variable is the start of where you can put addresses. In this case, it just ends up being an 8. From there, these are our writes. We're going to put those in. We're going to do write size short, doesn't really matter. And we send that payload. And from there, we should just get flag. We do this code normally from here. We just do a p interactive and we would just get out the flag. But since we need to brute force it, it's easier. It's hard to go into an interactive shell during a brute force. So instead, we just send the rest of the command. So we're going to say, hey, print out the flag, echo winner. I just do winner so that I can do a p receive until, because you don't want to be, I mean, I guess you could do a sleep since this is a winning condition, but it's easier just to receive until winner. So then you know that you have the flag. From there, yeah, we just save the flag as winner.txt and then we close. Like I said, this super useful tool, I've never used it before, but there's this built into Pwn tools is mBruteForce. So we pass it this wrapper thing. This function, mBruteForce expects a function that returns either true or false. And if it's true, it means it succeeded. And by default, it's just false. This means it hasn't done anything. Normally, you print, you would be giving it the alphabet. So this is going to compute all like arrays of length 8 with different alphabet characters and all permutations. We don't actually care about that. Really, we just need it to be called a bunch of times. But we're going to do it 32 threads, like I said, multi-threaded, which is super nice. And this is that little wrapper script. All it does is it calls remote run. And if it throws an exception, I print out the exception just because, and I return false. Otherwise, I return true. And so as soon as this returns true, it'll stop, and then we can check winner.txt. I'm not sure how long it'll take to run, but we can try. Let's go make Ubuntu 18. Python 3 solve. I think this is local. Nope, it's remote. Well, we'll let it run on remote, and we'll just see how long it takes. Thankfully, the CTF is over, so I most likely have the server to myself. But I think last time it still took a good 10 or 20 minutes. Oh, that was super fast. Wow. I thought I was going to be waiting here for a while. And sweet. So it said it found it. We go to winner.txt, and here it is. Damn, you got me again. I'm poor. So pretty fun challenge. Didn't expect to do a brute force, and I guess a lot of people didn't either. That's probably why it only had 8 solves. And I imagine a lot of people were trying. But yeah, it was fun. More real worldy, I guess. I think brute forcing ASLR and other things like that are more common in real world scenarios. But yeah, overall, very fun challenges. I had a good time. It was fun to play, and I'll see you at the next CTF. Cheers.